I'm Anders Miltner, and my collaborators and I worked on data-driven inference of representation invariants. Say I'm given an int set interface, requiring functions like empty, insert, delete, and lookup. I'm also given a specification of laws that I expect int sets to satisfy, like looking up in an empty set returns false, looking up an inserted element should return true, and looking up a deleted element should return false. I've implemented int sets using int lists. So now I need to prove that I satisfy the spec. Well, I immediately hit a difficulty. Our implementation of delete just removes the first occurrence of a number. So in our implementation on 0, 0, we return true, whereas the specification wants us to return false. So what went wrong? Well, the code is actually correct as written, because 0, 0 is not a valid representation of a set. Specifically, the list 0, 0 can never be built just using operations from the set interface, and is therefore not reachable. Fortunately, there's a standard procedure for resolving this. What we must do is we must find a representation invariant, a predicate over int lists that is sufficient to satisfy the spec, and is also invariant, or is inductive, which means that it must be preserved by module operations. If we do this, then we prove that all reachable int lists satisfy the spec, and we're done. This first step, we have to find inv. In this case, our invariant is going to be no duplicates. Next, we must prove that lists that satisfy inv also satisfy the spec. So where before we just had to prove that we satisfied the spec, now we have the additional assumption that inv is held on S. Last, we have to prove that inv is inductive. So we go through each module operation and show that the produced sets all satisfy inv. So if I run inv on empty, I will satisfy it. For insert, I take as input a set. So I can assume that inv is held on the input, and I have to show that after inserting value into that, I also satisfy inv. And we do. We do this for all of the operations, and then we're done. But this first step, finding inv, is actually quite hard. We have to find the correct invariant that is both sufficiently strong that we can prove that we satisfy the spec, and it also is inductive over module operations. Classically, this has been manually done. We introduce Hanoi, which takes as input a module interface implementation and specification, and outputs a representation invariant. Our contributions are that we've developed a data-driven algorithm for finding these representation invariants. We disambiguate inductiveness counterexamples using our novel notion of visible inductiveness. We've proven our algorithm correct, which means that given a sound and complete verifier and synthesizer, our algorithm is sound and complete over finite domains. We've implemented our algorithm as Hanoi, which uses an existing tool, Myth, for a synthesizer, and an unsound enumerative tester as a verifier. We evaluated Hanoi on a benchmark suite consisting of code from Cox Standard Library and Appel's verified functional algorithms. Our algorithm is parameterized by a synthesizer and a verifier. In a standard data-driven synthesis approach, the synthesizer proposes candidate invariants, inv, and the verifier proposes counterexamples, back. They do this communication using a testbed of positive and negative examples. For the synthesizer, this testbed serves as a means of specification. We need to return a candidate inv that returns true on the positive examples and false on the negative examples. The verifier takes as input inv, and then if it does not find that it is sufficient to satisfy the spec and inductive, it will return a counterexample, which we then can use to update the testbed. So our full algorithm starts with the testbed, goes to the synthesizer, and synthesizes a candidate invariant inv. We then take the inv and the spec and check if the inv is sufficient to satisfy the spec. If this sufficiency check fails, we get a counterexample which satisfies inv but falsifies the spec. Hence, inv is too weak, and so the counterexample is a new negative example. So if we return valid, so it does satisfy the counterexample, then we send it to an inductiveness check. So we check whether it is inductive or not. On a failure, this will return a positive or a negative counterexample. Or it returns an inductiveness counterexample, which can be interpreted in a positive or a negative way. If the candidate invariant is valid, then we can just return that candidate. So this decision of should we interpret the implication inductiveness counterexample as a positive or a negative example is a key difficulty that all of these data-driven invariant synthesis algorithms must tackle. Let me go into briefly this difficulty. So let's say I have a candidate invariant which is the length of the list is less than 2. The invariant is held on empty, but I try to prove that it is preserved over insert, and I find that I can't. Because if I insert 0 into singleton 1, I get the list 0, 1. Now, what went wrong? Well, this input of singleton 1 maybe it was accepted by inv, but maybe it shouldn't be, in which case it should be added as a negative example. On the other hand, 0, 1 was not accepted into inv, but maybe it should have been, which means it should be added as a positive example. In this way, this inductiveness counterexample can be interpreted in the negative or the positive way. Note that if we knew somehow that 1 was constructible, then we would know that it must be 0, 1 that should be added to the positive set, because 1 should not, a constructible value shouldn't be added to the negative set. So to be able to make this decision and have this knowledge, we add the additional constraint to our algorithm. We require that all the positive examples must be constructible through module operations. Then we can use our novel notion of visible inductiveness, which asks, can we find an inductiveness counterexample where all the inputs must be positive examples? So for this length less than 2 example, it is visibly inductive for true or for empty, and we try to prove it for insert, and we find that there's a issue. Insert 1, 0 equals 0, 1. 1 is part of our positive example set, 0, 1 does not satisfy the candidate invariant. So now, because we know that 1 is constructible, we also know that 0, 1 is constructible, because we made it through a module operation on a constructible value. So that means that it must be a positive example. Let's say we have something like the length of L is less than 3, with the positive examples of empty set and singleton 1. Well, if I ask myself, is inv held on the empty set, then I do get that. And for insert, I also actually get that. And that's because we don't have any positive counterexamples that can be used to prove this wrong. So this actually is visibly inductive. So visible inductiveness states that if given inputs from the positive set, the outputs satisfy inv, then inv is visibly inductive. Full inductiveness requires that given inputs satisfying inv, the outputs must satisfy inv. Visible inductiveness is just a step we go through, but full inductiveness is what we really need. So even if we are visibly inductive, we still need to do a full inductiveness check. So let's say we're checking if the length of L is less than 3 is fully inductive. It will work on empty. When we go to insert, it will not work, and we'll get the counterexample of insert 0, 1, 2 equals 2, 0, 1. Now, for this counterexample, we have we do not know if we should add 0, 1 to the positive set or to the negative set, or 2, 0, 1 to the positive set. But we have the constraint that all of the things in our positive set we must know are constructible. We don't know that 2, 0, 1 is constructible, so we must add 0, 1 to the negative set. So this brings us to our full algorithm. We add the constraint that the positive examples are always reachable. We add in a visible inductiveness check. On the counterexample for a visible inductiveness check, we use the positive side, and because at some points we guess that things should be negative examples, we use this as a place to start from a clean state and clear all of our negative examples. If we pass the visible inductiveness check, Then we do a full inductiveness check. And then we always take the negative side of the full inductiveness check. If the full inductiveness check is valid on the candidate, then we return that candidate. If our verifier is a sound verifier, then this algorithm is guaranteed to only return representation invariants sufficient to satisfy the spec. Furthermore, if our verifier is sound incomplete, our synthesizer is sound incomplete, and our concrete data type only has a finite number of elements, then our algorithm will find a representation invariant, if one exists. Hanoi is our concrete implementation of the algorithm. Hanoi uses Myth as our synthesizer. Myth is an existing tool for synthesizing recursive functional code. We need recursive functional code because that's how many of our invariants, including no duplicates, are expressed. And for our verifier, we use an enumerative tester. This suffers from being unsound, but it's fast and it's guaranteed to terminate. Furthermore, our theory doesn't address higher order functions, but our implementation, Hanoi, does, and it achieves this using higher order contracts. Our evaluation consists of a benchmark suite of 28 benchmarks, 5 from Appel's verified functional algorithms, 3 which take some VFA problems and add in additional laws and operations to the module. We took 14 benchmarks from Code and 6 from other benchmarks we thought would be useful. We ran our tests with a timeout of 30 minutes and inferred 22 out of 28 invariants. All of our invariants were correct, despite using a tester for verification. In this graph, the x-axis is the time, and the y-axis is benchmarks completed. Higher is better. In these comparisons, we compare against loop InfGen and linear arbitrary. We re-implement their techniques for addressing implication counterexamples. They work on different domains, so we didn't compare against the tools themselves, just their ways of managing implication counterexamples. Furthermore, in this, we found that we were able to not synthesize all of the invariants, and most of the ones that we weren't able to synthesize were some sort of a binary search tree invariant. We ran Hanoi on one of these benchmarks, just the basic BST implementation of a set, and found that we had a lot of difficulty in synthesis. So it spent a lot more time on this harder problem in synthesis. And actually the final synthesis call, which generated the final invariant, took over 20 minutes. So we think that improvements to the synthesizer would permit us to be able to synthesize more of these invariants in 30 minutes or under. So in general, invariant inference is an important research problem that's been studied for decades. I'm going to talk about a few of the more closely related pieces of work. In our evaluation, we compared against loop InfGen and linear arbitrary, which work on CHC solvers and loop invariants. And we tried to re-implement their ideas for how to address inductiveness counterexamples. And we found that in our domain, visible inductiveness works quite well. We don't compare, but other existing work in data-driven invariant solvers includes Horn Ice. Horn Ice is unique in that instead of making a decision of the positive or negative side of an inductiveness counterexample, they can actually give the inductiveness counterexample as a whole thing to a synthesizer. But they require then a synthesizer that can use those inductiveness counterexamples as inputs. Visible inductiveness can be kind of related to the notion of relative inductiveness by IC3. They both have this idea of kind of weakening the requirements for inductiveness a little bit from full inductiveness. IC3 itself differs from Hanoi in that it's not data driven, and then relative and visible inductiveness work in different opposite directions. So visible inductiveness starts from good states and propagates them forward. IC3 takes bad states and propagates them backwards. Furthermore, there's existing work in module invariants in the form of Derivaft. Derivaft takes a fixed set of predicates that it can learn and tests on them, and it also can't provide soundness or completeness guarantees. So in summary, we synthesize representation invariants with Hanoi. We do this using a counterexample-driven search via a communicating synthesizer and verifier. We use visible inductiveness to tame the ambiguity of inductiveness counterexamples, and we solved 22 out of our 28 benchmarks. Thank you, and I'm happy to take questions via Zoom.